All right. Hey, everybody. We're just about to get started. Still giving some people a little bit of time to get in. So we're going to wait maybe another 2 to 3 minutes. And then with that, we'll get cracking with all the content. I see people starting to log in right now. So yeah, we're just going to give them a few more minutes. In the meantime, I'm going to be sharing a link both in the Zoom, and if you're on the live stream with YouTube, I'll also be sharing a link there, which is a download link for the demo notebook that we're going to be showing off today. So if you want to follow along, you're going to want to download that in anticipation of loading it up. So just keep that in mind. I'll share that in a minute. But like I said, we're going to give people just a couple more minutes to log in, and then we'll get started. Thanks. All right, I think it's as good a time as any to get started. So first of all, thanks everyone who joined onto this webinar. I'm Rodrigo Aramburu. I'm one of the co-founders and the CEO of BlazingSQL. I'm also joined with Tom Dravas, who is here on the call, who is our principal data scientist. And Tom will actually be taking you through the notebook that he pre-built for this talk and for a few other things that we needed it for. So real fast, what I'm going to do just to talk about the agenda, I'm going to go over BlazingSQL and Rapids. This is for anyone who's not necessarily familiar. I've looked at the invitee list, and it does look like most people are relatively familiar with Rapids and the Rapids ecosystem. But just in case, we're going to do a quick overview of some components of the Rapids ecosystem, particularly as they pertain to BlazingSQL. And then we're going to just jump straight into the demos, which you're all able to follow along. For anyone who's not familiar with how we do live demos, I put a download link in the chat of this talk, or the chat of the YouTube live stream if you're on YouTube. And that just has a notebook, an IPython notebook or a Jupyter notebook file that you can download. And you're going to want to drag that into the free app. And for anyone who isn't familiar with Blazing Notebooks, our application, it's at app.blazingsql.com. And it's just a real easy way to get started with BlazingSQL and the whole Rapids ecosystem, because it's a hosted GPU with a private Jupyter Lab environment that lets you go and just get started. So great. With that, let's get started. So again, BlazingSQL, we're a GPU accelerated SQL engine. We're open source and we're fully built on the Rapids ecosystem. So let's just get into what that explicitly means. So the easiest way to really think about BlazingSQL is think about it as a SQL engine that works on data frames. So you can actually run queries on things like Pandas data frames, but our core data frame and the way that we actually, operate on data in memory is on the Rapids AI project cuDF. So if you're not familiar with cuDF, cuDF is very much like Pandas. It actually mirrors the Pandas API. The only difference is that it's an in-memory object that is on GPU memory. So having it in GPU memory allows it to be, incredibly low latency, incredibly high bandwidth, and also thousands of processing cores to be able to do massively parallel operations. And so this right here is probably the most basic example of what a BlazingSQL query could look like. Tom's going to go into relatively more complex examples. But what's really important here is if you're familiar with Pandas, this first line of code should look really similar to you. The only difference is that we've put in cuDF as opposed to PD or Pandas. And we literally are just reading this CSV file directly into memory. And what's great about cuDF is that it has a way of taking the header rows and understanding what the column names are, and then it does an inference on the data types. So this is how easy it can be to get started with creating a table inside BlazingSQL and knowing all the column names and things like that. So what you do then for Blazing is you literally just run this create table statement. We'll show the whole, how all of this actually works in the demo, but this is literally how simple it is. You just name it and then pass in the in-memory object, and then we can go and start writing SQL. That's literally all it takes to just get started and writing SQL. And what's interesting is this is running SQL on a fully in-memory, in GPU memory data frame object, which depending on your concerns or considerations and what you're trying to do might be exactly what you need, because having it inside GPU memory means that it can be it's basically as fast as it can get. Where BlazingSQL kind of starts taking this to another level, though, is you can actually create tables directly off of files. You can create tables off of files that exist inside S3 or Google Cloud Storage or HDFS or what have you. And you can be running these SQL statements directly off of those files without ever having to read them in, bring them in. And it won't be as fast as something that's in memory, but it'll let you run these queries. And it's still really, honestly, quite ridiculously fast. And so, yeah, that's what BlazingSQL is in a nutshell. When we think about the whole ecosystem, BlazingSQL doesn't really exist alone. It exists as part of a larger and greater ecosystem that's called Rapids AI. So if you're not familiar with Rapids, it's an end-to-end data science stack that's built entirely on top of CUDA GPUs. And so the whole premise of the stack is to basically enable incredibly high performance, right? Performance that just blows the mind at scale, and for a lower total cost of ownership. And we actually have some data to back that up that we'll be sharing with you. BlazingSQL, we already went through it, right? It's a distributed SQL engine that works inside Python. It's a conda installable package, and it runs on top of these GPU data frames and lets you run SQL. And then Dask is also a really great project that's really fundamental to this ecosystem. Dask basically allows us to scale things up from one GPU to however many GPUs we actually want in a system. And so in the example that Tom will be showing, he'll actually scale up a problem up to 8 GPUs in his demo, but we have users around the world who scale up beyond hundreds of GPUs and are able to run SQL queries distributed across 100 GPUs plus, depending on what it is that they're trying to do. This is a slide I actually just found again. I used to show this off a lot years ago, but we haven't really looked at, well, not years ago, because Rapids is only 2 years old. So like a little over a year ago, I was showing this off a lot. But the reason I wanted to show it for anyone who's not familiar is BlazingSQL basically looks a lot like what cuDF looks like. So if you look at cuDF, it's basically this layer to Python, and we just added a few different components into it, like our communication layer, this Apache Calcite, this relational algebra engine, these storage plugins that take SQL statements and convert them. Actually, what literally happens is a SQL statement will come in. It'll then go to Apache Calcite where it'll get parsed. Apache Calcite is an open source high performance SQL parser. And that'll then get converted into a relational algebra plan, which will then turn into a series of cuDF C++ function calls. So as cuDF gets faster, right, if someone pushes in a faster join algorithm, a faster group by, a faster sort on GPUs, then that immediately impacts BlazingSQL and BlazingSQL's capability of doing this. So we actually have one of our best examples is early on, an enterprise customer needed to be able to run SQL off of Apache org files and the stack didn't support Apache Orc. And so they built an Apache Orc reader inside cuDF. And all of a sudden now BlazingSQL can run SQL queries on Apache Orc files in HDFS. So that's really kind of what the power is of this slide and why I wanted to show it off. And then this is kind of what the whole ecosystem looks like. So the ecosystem actually has a lot more components now. This is actually pretty out of date because there's a whole bunch of other things that have been built, but this is kind of the bread and butter of the ecosystem. So on the left-hand side, we have our ETL and data prep tools. So we have SQL with BlazingSQL. We have data frame manipulation with cuDF. And then we start moving into more analytics, like machine learning with cuML. For anyone who's not familiar with these, so if cuDF is like pandas, cuML is like scikit-learn. So it also mirrors the API of scikit-learn. And if you're familiar with scikit-learn and like using scikit-learn with pandas, the transition process is really quite seamless. cuGraph is graph analytics, so it's network X, and it does the same thing. There's ways of plugging it in with deep learning, and there's also visualization tools and things of that nature. We've kind of been beating BlazingSQL dead with a stick, so I'm just going to hurry through this so that Tom can get started with his demos. But this is the way that you can think of a full workload where you have raw data in some sort of system. Maybe it's Amazon S3 in this particular instance. This is complete. This is all you would need to run a SQL statement on a data set that lives inside S3, for example. And what you then get is you get a cuDF. So this actually outputs a cuDF for the user. And you can then pass that cuDF off to anything that has integration with cuDF. So one of the earliest examples was XGBoost. The NVIDIA team built a cuDF integration with XGBoost. And now all of a sudden you could be doing feature engineering in your ETL process in SQL and data frame manipulations, and then hand off that data frame to a machine learning library. I want to show off just how we do at scale and what happens as you start scaling up. So TPC-XBB is a really popular big data benchmark. So it's about analyzing big data workloads, particularly on systems like Spark, Hadoop ecosystem, et cetera. And so right now, these numbers are actually out of date. We're going to be sharing some new numbers in a couple of weeks. I can't share them here because of a whole slew of different reasons, but they'll be coming out really, really quite soon that are going to just blow these away even more so. But when we're working with 1 terabyte of data, the current winner is Huawei with a configuration that they made on Cloudera, leveraging Hadoop and Spark. And they actually were running for about $282,000. We were able to replicate the workload with a system that cost less than half that. And what we saw, this is a log scale. This is a log scale y-axis. So we're seeing really quite huge performance improvements. This is about like 45x. These are in the single-digit multipliers of being faster. Purple is BlazingSQL, green is Huawei. But over here on the right, we have 200x performance improvements. Across the entirety of all the queries, we're running about 44 times faster. And I just chose basically the 2 best queries that we did, the 2 worst queries that we did, and one in the middle of the road, just to kind of show what these workloads look like. You can find these workloads on GitHub at rapids.ai/tpcx-bb. And what you'll see in the workloads is it's a big ETL step, typically followed with some machine learning step or natural language processing, and so on and so forth. So just to finalize things before Tom gets started, how can I get started? You can download us through Anaconda. You can get Docker containers that we already have, or you can leverage Blazing Notebooks, which is a fully managed turnkey kind of pre-built version of Rapids ready to go. So with that in mind, we're just going to let Tom get cracking. So I'm going to give you the rights to be able to share your screen, Tom, by making you the host. And
awesome.
then
Thank
you can get going.
Okay. Welcome, everyone. While we're starting up.
All right. You're now the host. So you should be able to take over.
Okay. Let me see if I can run this. Right. Okay, so welcome everyone. Thanks, Rodrigo, for for the nice introduction. I hope everybody we started with the fact that most of you know what Rapids AI ecosystem is, but that was a really interesting overview. Let me start sharing my screen. See if I can share this. Okay. Oh, I'm gonna have to quit now. Rodrigo, can you take over for a second? It looks like my preferences, they kick me out.
Oh, no worries, no worries.
Yeah, sorry about that. I'll be right back.
All right, so while Tom's doing that, I'm going to answer some questions. I was actually going to type out some answers to these questions, but I can just do it real fast. So Justin Miller asks, can Rapids run distributed across multiple servers as well? So I don't know if this question was asked before, I kind of mentioned it, but yes, it can. So we've run on systems that have, dozens and dozens of independent network connect servers, and they themselves have, between 6 to 8 GPUs inside of them. So we're talking hundreds of GPUs that are networked together, and you can make Rapids work across all of them. And we leverage Dask as the main way to do that. So Dask is what builds an awareness of all those network connected servers and those GPUs, and make sure that the jobs are running. So if you want to do cuDF-like jobs, which are pandas like jobs, then what we're talking about here, I'll start my video up, I realized, since Tom's re-jumping
I'm back. Yeah.
Okay, I'm just going to finish up this question and then you can get going.
By all means.
Where was I? So yeah, so that's how you do it. You do it with Dask, and that's how you can scale it up to as many servers as you necessarily want. And then, Tom, do I need to make you host again?
I believe you do.
All right, here you go.
Here's hoping that this works now. Okay. Okay, I think I should be sharing right now. Cool, all right. So sorry for that. So here we are. I have already downloaded the notebook that we're going to be using in the the free app that we have. So if you go to app.blazing.sql.com, you should be able to log in with your Google credentials and pretty much get started with everything that we have prepared for you today. I already downloaded the notebook itself. I believe Rodrigo has pasted the link to the notebook in the chat. So if you haven't done that, go ahead and do that right now. I will create a folder for myself in the root of the app, and then just drag and drop the notebook itself there. So you should be able to see see this screen and also follow on your own pace in the app if you log in. So what we're going to be talking today about is the parking in Seattle. A while back, when I was playing with cuDF, I was looking for some data on the web, and since I live in Seattle, I stumbled upon the City of Seattle Department of the Transportation. There's a big open data portal where they effectively allow you to download parking transactions. These parking transactions are collated annually, so you can go as far back as pretty much 2016, and that's where we're going to start in the when we're going to showcase the larger data set. But for this particular example, we have already uploaded 2 months worth of data, into S3, and that's what we are going to be using in this particular instance. What the data contains is roughly every single transaction that happens when you go and find a parking spot and you swap your card in the meter. There's roughly 1,500 block faces, which is effectively translating to, okay, I can park along this road in Seattle, and that's what the data showcases. You will also notice as we go through the examples that there is no data for Sundays, because the parking on Sundays is free in Seattle. So first things first, we're going to start with loading the modules. We will download the Blazing context from BlazingSQL. We will also, as Rodrigo was mentioning, we will be using a CUDA cluster. So in this particular case, we're going to be using Dask. Dask provides 2 ways of creating your client. So when you start Dask cluster, you start effectively a Dask scheduler that acts as a head node for the whole for the whole cluster that your client will effectively interact with. What you say, what you then do is just literally connect the client to the head node, and the head node will translate all the requests that go into the head node and then distribute that work to all the clients, all the workers. We of course import also QEF. We're gonna use pandas. We use pandas effectively to just set up this display max rows. We want to show this particular option from pandas allows you to show up to 100 rows. And then effectively we create the local CUDA cluster. This is a different, so if you have a cluster that is spanning multiple machines, you don't necessarily want to use the local CUDA cluster. Local CUDA cluster is useful when you have a single, a single machine with either one or multiple GPUs. Then you can create a local CUDA cluster that will implicitly start the task scheduler on your machine and also instantiate as many workers as the GPUs you have on your machine. Now, I will ask you to take the pool equals to true out. I forgot to do that. But once you do that, we can run the first cell. And what happens right now, we're going to instantiate the Blazing context. So what, Blazing context will do, it will go to all the, to the head node and all the workers and instantiate the Blazing context within each worker. So now that we have the BC object, we can use one of the storage plugins that are already built into BlazingSQL and connect to a BSQL bucket from S3. If you execute this, we already have registered the bucket with the Blazing context, so we can start accessing the data that is present in the bucket. Now, this particular bucket is a publicly available, so you can go there and then just access this data without authenticating. If you have a bucket that is your private bucket, you can also register that with BlazingSQL by simply providing the secret keys within the call, and that way you can access the data in your own secure way. Now let's have an overview of how we create the tables. I know, because I uploaded the data, that in this particular location, in data, Seattle parking and parking May, June 2019, I have a parquet file that is partitioned into 40 partitions. So effectively what I'm doing here is I'm creating a list of 40 paths to S3, so I can actually register that table later on with the BlazingSQL context. We also have the parking locations, table over there. Now the difference, the way we did this is the way the data is published from the Seattle, parking, the Department of Transportation, the data set itself. Every single row in that particular data set has all the metadata about every single parking, spot that was literally, the transaction took place on, which seems a little bit wasteful. So we decided that, okay, well, we're going to separate that and then create this, more database feel where we can have just a small set of 1,500 rows in parking locations that will carry over all the, all the metadata about the parking location, and then have a key that we can join back to the transactions that will be trimmed down to only the necessary columns. So if we run this, it will effectively create all of these particular objects for us. Now, this particular data frame, this is purely to, later on for visualization purposes, to map the date of the week 0 to Monday. So this is really not necessary to explain. So this table is created. This will be a QDF table. Now, this particular cell right now, when you start executing that, it will create and register the tables with the Blazing context. So we're going to have access to a table that is called parking transactions, parking underscore transactions, that we got from the parquet file that is on S3. We have created a parking locations table and the date of the week table as well. So we're going to have access to all of these tables from now on, moving forward. The way I normally start working with data, I start to get, I like to start to get some familiarity. with the data itself. So first of all, I want to see what I'm dealing with. So in this particular case, the SQL transaction here is selecting 10 random records from the top, pretty much 10 random records from the parking transactions table. So now we have those top 10. Let's see how many, how many records we're dealing with. So how many records do we have in the table for the 2 months that that we've selected from the data set? And then when you run this takes a little bit longer, but we have around 49 million records in those registered in the data set that has 2 months. Bear that in mind, because we're gonna scale it up way beyond that when I showcase you the larger one. In terms of columns, we have 4 columns. The occupancy date time, which is effectively a when the transaction took place; paid occupancy, which indicates how many total spots were occupied at that point in time. Source element key, this is our key. We're going to be joining that to the metadata about the parking locations. And the day of the week, which is a column derived from the occupancy date time. If you want to look it up, the date types we deal with, remember when Rodrigo told you that any bc.sql transaction returns a QDF, we can quickly use that functionality from QDF to see that occupancy date time is a datetime 64 column, and paid occupancy and source element key are int 64s, and day of the week is int 8. In terms of looking in and peeping into what the data really looks like, if you actually run this way, it will because we are using Dask cluster, it will return just literally a Dask data frame structure. So it will tell you, okay, well, this is what my plan is, or what I'm going to do if you tell me to do it. Right now, we haven't executed anything. If you were to look into the BlazingSQL, Dask dashboard, you would not see any movement over there. As soon as you start, add compute, you tell Dask to finally execute this, and then you can get a QDF back. Only at that point, the Dask will actually execute the query that you did. And then we're going to go in the same fashion through the parking locations. So parking locations, this is effectively the whole list of descriptors of the parking location. So you can see we have 1,500 records roughly around there, and 9 columns. The list of columns is we have our key that we can join back to the parking transactions, but we also have block face and side of the street and parking time limit category and so on and so forth. All of these, we have the same times. I'm not going to go precisely through every single column over here. One point that I want to draw your attention to is the location. And when you actually run this table, this cell here, you can see that the location is in a format called WKT, well-known text. And effectively, it's an encoded, Latin long location of that particular parking spot. And we're going to use that later on to find what is the nearest parking spot to the Space Needle within a certain radius from the Space Needle that we have the highest chance to find a free parking spot on a given day of the week and around some particular point in time of the day. We do have some duplicates in the parking locations. So this particular command, the cell here, effectively drops the duplicates that we have on the source element key. It's not a big deal. So when I mentioned the the parking locations, when we work with the parking transactions, our ultimate goal is to find, okay, well, I want to go to visit Space Needle. I want to go to see, park somewhere downtown in Seattle. I want to have a look. If I plot in the coordinates of where I want to go, can you tell me at this point, on Wednesday or Thursday around 1 p.m. what are the closest closest parking spots that I have the highest chance of finding the parking there. So what we're going to do is just like in the SQL way, we will extract the year, month, day of the month, and hour from the occupancy date time. So this is effectively, straight up SQL, query that you can look up online, and then, BlazingSQL supports all of this. And right off the bat, that takes, a couple of seconds to do. So we can now check how many transactions we get per day, right? So if you look at this, we can see that we have roughly somewhere in the vicinity of 900,000 transactions per day. So every single day we see around 900,000 transactions happened, being processed by the city of Seattle or from the Department of Transportation. So if you can calculate the mean from the counts table that we have created over here. And by the way, so this is just to draw your attention to how fast this is. We have right now literally went to 48 million rows table. Parking transactions has 49 million rows, and did a aggregation on year, month, and day, plus, we counted how many rows we have there, and it only took 1 second. The way we featureize parking locations, what I want to do, ultimately, we will have to calculate the distance. And in this particular example, we will be focusing on the hover sign distance, i.e. just the straight line from where we want to go to a parking location. In order to do that, we actually need to get out the latitude and longitude from the point, the well-known text format object that we have there. So the way we do it right now is we are finding if you were to print out that particular that particular example of the well-known format, you would see that there's a point, and then in parentheses there is the longitude first and latitude second. What we do is we find, and they are separated by space. So in this particular case here, we are finding that space, where the location of that space is, and then that gives us this delimiter location. That gives us where we going to start extracting the latitude. So in this particular case, we're using a substring, substring functionality from SQL that we say, okay, we'll take substring, take location, start at this particular location, and then give me as many characters after as the length of the string is minus the delimiter location. So effectively we extract that. For the longitude, we start at 0.8, so we pretty much do the same thing. But we start at the character number 8 because that's effectively the first character after the opening parenthesis, and then we extract the subsequent number of digits. So if you run this, we can now calculate the average occupancy at every single parking spot, right? So what we do is we will actually, this is an example of how flexible and how SQL-like BlazingSQL engine is. You can have not only just query the data, but you can execute quite sophisticated complex queries against the engine itself, and it will understand that, right? So in this particular example, we have an inner query that is actually going to this 48 million rows parking transactions table, does a left outer join on parking locations where we extract the source element key and then parking space count from that particular location, right? And then we join that on the source element key here. So that's our inner join. I call it an alias for this is an inner table. And then what we do then is we effectively recreate the parking transactions. So what we do, we append additional information to our parking transactions table, where for every single row in that transaction, we will have the average occupancy at that particular point in time, which is effectively the paid occupancy divided by the parking space count. We didn't have the parking space count in the parking transactions, so that's why we do this left outer join in order to bring it over from the parking locations table. So if you run this, once again, this is 48 million rows joining to a table that is 1,500 rows, and it takes 1.28 seconds to do all of this on a GPU, on a single GPU or in memory, right? So we now have a source element key when the transaction occurred. We have the paid occupancy and parking space count, the average occupancy, day of the week, and hour of the day. So now if we wanted to, what we really want to is look at these past 2 months, and for every single source element key, day of the week and hour of the day combination, calculate what it was the average occupancy at that point in time on that particular given week of the day of the week, and on that particular source element key. So in this particular case, we literally pipe the QDF that gets created by calling bc.sql and create on the fly a new table that we call means, and that takes half a second. So once this is done, now we have access to the means table. What we can do right now is to just calculate the average per day of the week and per hour. What does it really look like, and is there any any seasonality that we see in the data? So if you run this, you can quickly, from the mean occupancy QDF, richly run that query, convert it to pandas, set the index to be day of the week as a string. So the thing that we did here, as I mentioned before, when we created the day of the week table, we left out a join to the day of the week table. And then instead of carrying over and then presenting later day of the week as a number, we actually encode it to a string. We take the mean occupancy column there, and then we effectively use, right now at this point in time, we are back in the host memory. So because we've converted to pandas, we can just quickly dot plot that data. So in this particular case, as you can see, we have a strong day seasonality, right? So we can see that the parking occupancy peaks around midday, then trails off a little bit for the afternoon where people go back home, and then it comes back for the night, the evening hours where people might go out and go for to see a movie, or go for for dinner in a restaurant. You can also see that when we start on Saturday, that's an effect of Friday night. So there's a much not much higher, but substantially higher parking occupancy on Friday evening, where you can see, and then it quickly trails off for Friday for Saturday night. So people go back after spending the night in downtown Seattle. So now that we understand the data, we know what we want to do. Let's find the best parking spot. So as I said, we're going to go to the Space Needle in Seattle. I've looked up the lats and long for Space Needle in Seattle. So we're just going to append that to our parking locations table, right? So right now we have lat and long for every single parking location in Seattle. And then we have the reference point to where we really want to go. So that's this particular column and these two columns are the same for the whole table. And we're going to calculate the hover-sign distance to every single location from Space Needle. So the way we do it is effectively we're using the hover-sign distance formula, where we convert the lats and long to radians, and then calculate the differences between lats and longs, and then use the effectively the hover-sign formula, which is encoded in this line and this line, in order to calculate the distance in feet, in this particular case in feet, to every single parking locations from Space Needle. So when you run this, this takes just a little, tiny little time. We can drop the table right now. So this table effectively goes away, and you no longer going to have access to the temp table that we have registered before in this particular cell. And then what we're going to do here right now is we assume that we want to travel to Space Needle on Thursday around 5 p.m. We're going to left outer join to our means table, where because we want to carry over this mean occupancy. We want to later on sort by the distance in feet, but also we want to carry over this mean occupancy, mean occupancy column over. So when you compute this, it takes 0.2 seconds, and it tells you that, okay, well, the closest parking spots to Space Needle on Thursday, 5 p.m. Within 1,000 feet radius and with the mean occupancy less than 50%, are these 6 parking locations. So if you're willing to, walk a little bit further, so 900 feet to 3rd Avenue between Clay Street and Broad Street in Belltown, you have a really high chance of finding a parking spot over there, and then you can go and then, explore Space Needle. So, long story short, if you were to run this notebook by literally going to, run from the top to the bottom, you would be processing 49 million records and 1,500 records in the other table, and it would take you roughly 5 to 6 seconds to go through the whole notebook and get the answer that you want. So that's pretty much almost, real-time processing, using BlazingSQL engine. Rodrigo, what do you think? Should we pause here for any questions, or should I go ahead with the large example?
Yeah, I've been answering questions as they pop up, so you can go to the other example. That way we have a little bit of time for Q&A. So you might want to jump in, scale it up, and then we do some Q&A.
Sounds good. Okay, so I started this cluster earlier today, so it shouldn't take too long, but I started this cluster. This is the new, beta version of BlazingSQL, where you can go back to the app that we've been using so far, but you can also create your own private GPU cluster, right? And then if you click on this particular, if you really have, you've purchased some tokens, purchased credits, in this view, you can create a private GPU cluster. We can, name it Tom Webinar, for instance. And in terms of size, we provide you effectively, from the smallest to the largest, right? So you can have a GPU, your own private GPU with 1 GPU, 2 GPUs, 4 GPUs, 8 GPUs, 16 up to 64. And additionally, if you leave your cluster unattended, simply because, of course, you don't want to pay for the cluster if you don't use it, you can choose that, okay, if we have noticed that you haven't been doing anything on the cluster for 5 minutes, for 15 minutes, for 30 minutes, or up to 1 hour, we'll automatically shut it down for you, and then you stop charging you for that. So this is the way you can actually, take whatever you've been working on the free instance and move it over to, to your own private GPU cluster, where you can scale it up to a, the actual workload that you need to support. So in this particular case, we are already up and running. You can click on Launch Jupyter. It will take you to a familiar spot, with, pretty much the same, with the same, almost the same notebook, right? So in this particular case, I have a large, this is the large example, right? And I'm going to walk you through the differences between what we've already shown in the small one and what is the difference here.
You want to update your client IP, by the way.
my client IP. That's good color. Yes. So let me do this. Okay. So my automatically when you start the cluster itself, it will start. Because you are on a private one, and in this particular instance, this particular cluster that I'm running that off of is in size large. So I have 8 GPUs to utilize. Okay, go away. Sorry. So we automatically start a task scheduler, right? So in order to connect to the task scheduler, for those of you who are not familiar with this, 8786 port is the port that the task scheduler is normally listening on for any connections from both the workers. If there is additional worker that wants to register with the task scheduler, they would ping the scheduler on port 8786, and that way they are able to register themselves and say, "Hey, I'm here. I can do some work." If you create a client, we also pass the IP address of the where the task scheduler is running and the port 8786, and that way we automatically create a client against an already running task scheduler. The client restart effectively tells the scheduler to dump all the memory, that whatever you have in there, just dump it and then start from scratch. So effectively, it just wipes out all the memory that you have, occupied by any other objects, and then it gives you a kind of clean slate here. Now, you notice that I'm using a pool equals to true in this particular occasion. This is to, effectively what BlazingSQL will do is it will register or kind of like, create this pool of memory, the GPU memory, that we can quickly, we have a very, very quick access to. So when we register tables or we do any, querying, it will effectively, do it more quickly instead of just, constantly allocating and deallocating the memory. So let me run this. This shouldn't take too long. And we're going to have the BlazingSQL context back. Now, if you wanted to have access to the dashboard in the back that's running, the task dashboard, you effectively can go just to the IP port, the IP address of the running cluster, and then access that through 8787. That's where the task dashboard is effectively running. So right now, what is happening? The client is going out to every single worker and instantiating a Blazing context on every single worker. It's because we started from scratch, not all the workers might have registered already. So I'm going to run this again. So we're going to create connect to the client and restart the whole cluster again. So it's for me as a safe case that I definitely have access to all the eight GPUs that I subscribe for. In a similar manner, I'm gonna register my S3 bucket. This is the same bucket that we have used, but in this case, I will be using a the Parking Seattle data set that spans pretty much 4.5 years, because we are midst. I think the 2020 is up to July, if my memory serves me right. So in this particular case, I'm just going to pump through this. This is the same thing we've already seen. We create the tables, so same parking transactions, parking locations, and day of the week. Same deal. So we select 10. So right now we are selecting 10 transactions from a much larger data set. So that will take a little bit longer, but not that much. So that took 11-12 seconds. Now this will take a little bit longer, and you can actually see a little bit what's happening behind the scenes. So what happens right now is, when we execute that cell, Blazing context will go to every single worker and then, ask it to do, okay, give me a count. From every single partition that you have, give me a count, right, from every partition. And then we say, okay, we have 1.3 billion records in this particular, this particular data set. List of columns doesn't change, except for we now have a null dusk index. That is, an artifact of saving the data set into the Parquet format. You can run this transaction sample and compute that. It exactly looks the same as the previous example. The parking locations hasn't changed, so I'm just going to quickly pipe through this. We still have 1,500 records in this particular table, and it still looks the same. And we still drop some of the duplicates there. Now, featurizing parking transactions. You remember that we've extracted year and month. We also extracted other things, but for this particular example, I'm not going to do that. And I will just, in order to create this view, in this particular case, we are creating a table that summarizes the number of parking transactions per month, right? So what we're gonna get back is a QDF table, Dask QDF data frame named counts. And then what we're going to do after that is we're going to compute that, move it to pandas, set index to year and month, and then do a plot. So, okay, there we go. So as you can see, every single day, we have roughly, 25 million transactions in every single month. You can see that there's something happening, right? So this is the beauty of the whole, for me, at least as a data scientist, a beauty of working with rapids. Every single time I can run a query very quickly. It took me 12 seconds to chew through 1.3 billion records on an 8 GPU cluster that costs me $8 to run per hour. And I can straight away see that there's something wrong with the data that it has piped through for 2020, right? I can trust the data up to probably March, but after April, May, and June, something's wrong. This might be quite easy to explain. Not necessarily something that is really wrong with the data, but it might be just the effect of the restrictions that were in place for COVID, right? So in April there would be much less people traveling and parking in Seattle. Or I haven't checked that out, but maybe city of Seattle actually lifted all the fees for parking. That I don't know, but you can tell straight away that by simply looking at the data, by summarizing in the data, and working almost in real time with the large data set, that you can quickly spot some problems with with the data that you're working with. Similarly, if we featureize the parking locations, once again we are going to a 1.3 billion. Oh no, this is parking locations. So this is 1,500. Oops. I run it one time too many. Similarly, we create, we want to calculate the average occupancy. So right over here, you can see a quite complex query with two inner tables. I have the original inner table that gives me the average occupancy. Then I calculate the additional check. So for some reason, there are instances in the data set that you have more people parking than there's available spots. It might be data fluke. It might be just the way that the data is aggregated by the Department of Transportations. So in this particular case, I'm saying that okay, anything that is above 100%, just trim it at 100%. And then we quickly create, this is the step where we create the means table. So we do day of the week, source element key, hour of the day, and the mean occupancy. So if you run this on 8 GPUs, 1.3 billion records with all of this quite complex query to run, it shouldn't take more than a couple of seconds. let's see what's happening. There you go, 16 seconds, and we have the means table. So right now, what you can do is to literally go back to what we've been doing so far and get the results back. So right now, based on the query that we've done, we still try to go to day of the week 4 and then hour of the day 17, so 5 p.m. on Thursday. But now the order might have changed, and also what we see that the mean occupancy has updated, because we are looking right now at a much larger time span. So this particular way, we can build more confidence, and then we can do more with the data that we have. So as I said, like this is precisely what I really value both about pretty much the whole Rapids ecosystem. I can iterate over this data. If I make a mistake at the very beginning, it literally took me to run this whole notebook. I was clicking through, but if I were to run all cells in this notebook, it would take me 20 seconds or 30 seconds, which is nothing, to process 1.3 billion records and get a result that I might not like, or I might have made a mistake and then something didn't work. And I can go back and then in the next 30 seconds fix what I didn't like, and in the next 30 seconds I have the results back that might match my my expectations. Or I can experiment, right? I can change things. I can if I'm building a regression model, if I'm building a classification model, most of the time what we do building a machine learning model, we need to build different features. We need to derive from columns. We need to sometimes we do take a logarithm of a numerical column, or we combine columns together in order to to do something and to build a new feature. I can iterate over this step in much quicker way than I was able to to do before on a much larger cluster running on purely on a CPU. All right, so I think that's it from me. Rodrigo, I'll probably hand it over to you, back to you, and then we can have some Q&A.
Yep. So we only have a few more minutes. I've been answering questions as they're coming in. So if you're at all curious to see what people have been saying, there's a Q&A section.
Okay.
Let's see. Pablo Tercero is asking, are there more spec stocks on the private clusters? Yeah, so that's something. So there, for an extra small, you effectively get a 1 GPU instance, and for our largest size, which is a 4x large, you can go as much as 128 GPUs, which have 2 terabytes of video memory. Over time, we're actually going to be benchmarking all of these cluster configurations for people, so that they are going to be a little bit fluid behind the scenes, and the user won't necessarily mind so much what's being put up for them, as much as how much data can it process, how quickly can it process. So for example, we use really heavily the Tesla T4 GPUs right now because we see a ton of cost benefit that shows them really working incredibly well. But there's a new A100 GPU coming out that we think will be able to let us make some really large clusters incredibly performant, that'll be even more performant than that 128 Tesla T4 system I was talking about. So we're going to be changing it up a little bit behind the scenes. The way you should really think about it, though, is that every size is basically 2 times larger than the size that came before it. So a small is twice as fast as an extra small, a medium is twice as fast as a small, and so on and so forth. Are there any other questions? So while I let just like another minute for people to ask questions if they want to, I wanted to say, Tom, brilliant demo as always. I loved seeing it. You all could kind of see how quickly and easily Tom was able to take a workload that worked on a single GPU and just launch a larger GPU system, start querying on it, go from 49 million rows to 1.3 billion rows. And yeah, I mean, that was just super duper impressive to me. And you could see how easy it was to get started.
Correct, and it's still interactive. So that's the biggest benefit for me, right? It's still interactive. I don't have to wait, half an hour or an hour. for the system to tell me that I made a mistake and I need to restart that, right? I know the answer to the questions that I have against the data almost instantly, and that way this is the largest benefit coming from being able to process a humongous and large data set, but also very quickly, right? So I can iterate over I have 1 million ideas every single second. So I can put those ideas and then questions against the data and then get the answer almost instantly.
Yeah. All right. Well, with that, we're at time. So if you have any further questions, you can follow us on Twitter. Twitter is the best place, at BlazingSQL, to hear about the latest and greatest. We tweet all the time, any updates, everything that's coming out, and so on. So that's a really good place to look at us or look us up. Also, the Rapids Go AI. So for anyone not familiar, Rapids has a Slack channel. If you go to rapids.ai and go to their community tab, I think you can find an invite link. But that Slack channel is the best place to talk to all people or all things revolving around Rapids, and all the core contributors and maintainers of the ecosystem are available inside that Slack, that Slack for you to be able to talk. And yeah, anything else, please. You can also reach out to us directly, Rodrigo at BlazingSQL.com, Tom at BlazingSQL.com. And we're going to be doing a lot more of these talks. So in about 2 weeks, we hope to have another webinar planned. We'll post stuff about that later this week. And thanks a lot, everyone. Really hope you appreciated it and expect to hear more soon.
Fantastic. Thanks, guys. Appreciate the time. See you next time.
Thanks. Tom, you can end the webinar since you're the host now.
Oh, gotcha. Okay. All right. Well, thanks very much. And we'll see you next time. Bye.